Hello, friends. My name is Jonathan Allen. I'm a physicist and have spent most of my career in developing solar energy and working on high power electronics. I did my thesis on environmental stuff, measuring the earth particles. So I've had an interest in environmental stuff most of my professional career.
Jonathan, is there a microphone?
I don't know if there is.
I can hear you, but people in the back may not.
I don't see a microphone here. Well, people in the back might want to move forward then, so they can be doing business. Anyway, most of the present. So our topic here is how green is an electric vehicle. We're going to talk about the energy and environmental impact of electric vehicles. Most of the present transportation vehicles are powered by the burning hydrocarbon fossil fuels. That combustion oxidizes the carbon to CO2, carbon dioxide, which then gets released to the atmosphere, where it enhances the Earth's greenhouse effect, blocking the escape of heat to space and warming the Earth in an irregular sort of way and disrupting the environment and weather patterns in what we've discovered are quite destructive ways. Hurricanes, for instance, are far more intense than they used to be because of the greater temperature difference between the warm ocean surface and the cool top of the troposphere. Think of it as a heat engine operating between two temperatures. Anyway, mitigating CO2 emissions is the main reason for promoting electric vehicles. The transportation sector, is that arrow showing up on the screen?
Yes.
Yeah.
Okay, the transportation sector, where it accounts for 38%, or the biggest chunk of our CO2 emissions in the US, and we're not that much different from other industrialized countries. About 80% of this is motor vehicles. Autos, trucks, and buses. The remainder is railroads, ships, and airplanes. So motor vehicles also have a huge carbon footprint. Maybe should we say tire track? Power generation is also a big CO2 emitter over here. But we are reducing this as we convert our electric utilities to clean and renewable energy. Let's make, first of all, before we get any further, let's, as a physicist being my racket, I have to make a clearer definition of separating the meanings of power and energy. Let's make an analogy. If you have water pouring out of a pipe, the rate of flow in, say, gallons per minute is power. The amount you've accumulated, the total integrated flow over a period of time, is analogous to energy. Now, not all energy is equal. Work, including electricity, is a higher grade of energy. Work is the measure of the force times distance associated with moving, say, an object against a resistance. And electricity we measure in volts, amps, and watts. But the interesting thing is that electricity and mechanical work are interchangeable with no thermodynamic limits on the efficiency. They are the electric motors and generators approach 100%. Heat, however, is another bag. And here we have the Carnot equation. Sadi Carnot in the early part of the 19th century is now regarded as sort of a father of thermodynamics. He was mostly interested in analyzing the behavior of the newly invented steam engines of the time. But its theoretical material still applies today. The maximum efficiency you can possibly get by taking heat from a hot reservoir, TH, and having it flow through the engine to a cooler reservoir is equal to TH minus TC over TH. These, by the way, have the absolute temperatures, not Fahrenheit or Celsius. units are Kelvin. So room temperature here is about 300 Kelvin. Remind me of a TV weather announcer who said, yesterday the temperature was 20 degrees. Today the temperature is 40 degrees. The temperature has doubled. My wife and I were standing behind a fence, and 12 inches of me was sticking above the fence. Only 6 inches of her was sticking above the fence. So I'm twice as tall as my wife. Getting back to business though, when work is dissipated by friction, say a spinning flywheel has a mechanical friction brake applied until it comes to rest, that energy converted to heat ain't going back to spinning the flywheel back up to speed. The Otto cycle engine, as opposed to the Carnot cycle, which is purely theoretical, we don't have real engines working on that cycle. The Otto cycle, which named for Neil Otto, the inventor, which is used in the 4-stroke gasoline engine, has an efficiency of about 20% most of the time. You might be able to squeeze 25 out of it under the best conditions. Now, electric vehicles, while underway, not only avoid hydrocarbon fuel and CO2 emissions, they also avoid the low efficiency of that Otto cycle. But if the electric power comes from a thermal source, like a combustion power plant or a nuclear plant for that matter, the second law limits on efficiency start to kick back in. For the sake of completeness, let's talk about the various kinds of electric vehicles. The 4 types that we have are battery electric vehicles, which are our main topic. Those are automobiles propelled by an electric motor, which carry an onboard battery, which you charge up from an external source. You drive and then recharge your battery as necessary. There is no engine on board. Then there are hybrid electric vehicles, the best known of which is probably the Toyota Prius. We have one that we've had for about 17 years and we've been very happy with it. There's a gentleman here who has one with 300,000 miles on it. He obviously has been happy with his. Hybrid electric vehicles also have an electric motor, but the electric motor's function is mainly just to assist the gas engine. For instance, when you need a big surge of power, you don't have to open up the throttle of the gas engine fully. Part of that power comes from your electric. And similar, also they can give you the benefit of what we call regenerative braking when you're slowing down. And we're going to get into the details of that later. Then there's a plug-in hybrid, which is very similar to the regular hybrid, except in this case, the battery is big enough that you can drive some miles without having to start the gas engine. So if all you're doing is commuting about town, short distances, maybe 10, 15 miles or so, you would theoretically never have to crank the gas engine. But if you do start going further distances, the gas engine will cut in and it behaves just like a regular hybrid. The final one is a fuel cell electric vehicle. And here you have a supply of hydrogen, either compressed or liquefied, which is oxidized in a fuel cell. When you oxidize hydrogen, you get hydrogen dioxide, H2O, which is called water. In fact, the word hydrogen from the, I believe, Greek means water maker. We're going to concentrate, as I mentioned before, on the classic battery electric vehicle, although some of the information will apply to the breeze. First, electric vehicles are not new. This is a 1914 Baker electric car. You can see it's an automobile. It's got 4 wheels. It has, but do notice also that it does not have a radiator. The power is stored in a battery. In this case, a conventional lead acid battery. The motor is a brush type DC motor, and you can drive it for modest distances. Moving up a few years, we have a 1918 Detroit Electric, and the driver, if you can recognize his face, is Jay Leno, who's a famous comedian and is also famous for restoring and collecting antique automobiles. And this is obviously one of his fleet. And according to what I've read, he actually drives this around town to do shopping and short trips. The original electric sold mostly to people who had some money to buy one and had to travel within town, often getting underway promptly. And doctors were a big customer. They were also popular with women since they did not require hand cranking, which is a fairly muscular operation. The latter reason began losing significance after Charles Kettering invented the electric stove in 1912, and we still use it today. A more recent development occurred in the 1970s when President Jimmy Carter, concerned about the environment, fossil fuel depletion, and our dependence on foreign sources of fossil fuel, got the post office to adopt a number of electric delivery vans. And here we have an electric postal van from 1980. These were fairly simple design. Again, the ones I know about use lead acid batteries and regular brushed DC motors. And while they had limited range, they were still well suited to postal routes, which are relatively short. But with lots of stop and go driving, which electric vehicles just love. The next president, whose name we do not utter in polite company, terminated that program, along with all support for renewable and solar energy. And he famously removed from the roof Carter's solar thermal panels. So he got the post office to just sell off its electric vans on the surplus market. Well, a friend of mine in Massachusetts, whom I known since I was a little kid, bought one. And he lived about 8 or 10 miles from where he worked. He owned the place where he worked. And I, at the time, was working at Cronow Corporation right here in New Jersey, where we were manufacturing amorphous silicon photovoltaic panels. We had some slightly substandard panels that you couldn't sell regular. And so I was able to arrange for him to buy them cheap at a discount. He set up a charging station outside where he worked. And every day he would drive to work, hook up to the charging station, drive home, and the next day repeat the cycle. And so he had a totally green commuting system to go to work and back. Recently, the Postal Service's interest in electric vehicles has revived. As I mentioned, postal fleets are a perfect candidate for futures. They run predictable routes, making it easy to place charging stations and schedule your charging times. Their frequent stops with braking and re-acceleration exploits the regenerative braking and dynamic properties of the electric motor. We're going to go into the theory of regenerative braking shortly. In March 2022, the post office did an analysis where they found that 99% of their routes are less than 70 miles, which is well within the distance that the prospective EVs will run on a charge. These days, with our rising concern over climate change and concern about reliable petroleum supplies, the need for EVs and the technology that will benefit has advanced considerably. Here we have a sketch of the basic electric vehicle. And if you look at it, you're going to have down here is the battery, which is a big flat thing that lives in the bottom of the chassis. And that's a good place for it because it lowers the center of gravity. And then you have your electric motor, the transmission, which is not clearly visible here, the battery converter that takes the several hundreds of volts in the traction battery and converts it down to 12 volts for this little battery, which we then use for the usual stuff like headlights. And then you have an onboard, you have a box which is an onboard charging device, which so you can convert the power mains into the DC you need to charge up your battery. The ability to charge from either AC or DC sources gives a wide range of opportunities and locations to charge. The motors in electric vehicles are either variable frequency three-phase AC motors, thank you Nikola Tesla, or brushless DC motors. Brushless DC motors are generally better. They are more compact with a higher power to weight ratio than the variable AC. And their efficiencies are 90% or better. They also have a huge dynamic speed range. That is the ratio of the maximum speed at which they can spin and the minimum speed at which they can perform. And that is 90 to 1 typically. Compare that with your gas engine, where 3 to 1 is about the best you're going to do, maybe 4. Since the motor is self-starting as soon as you apply voltage, and the rotation is reversible by switching the polarity of the supply, you have no need for conventional rotary speed and reversing transmission, either manual or automatic, nor for a clutch. All you need is a set of reduction gears to take the thousands of RPM at which your motor is spinning and gear it down to the much lower speed at which the wheels on the vehicle have to spin. The electric car can either have one motor with a differential or separate motors, one for each driving wheel. This is a little more detailed schematic diagram, although it does not show the physical placement of things. And here you can see you have connected the battery, going to the motor controller, brushless DC motor, reduction gears, and here you have a differential to run both of your front wheels. This is a front wheel drive car that most of them are today. It also, by the way, has conventional hydraulic mechanical brakes. So the idea is when regenerative braking is not sufficient, that kicks in. I'm going to get into it in a little while. To control the DC motor, we use pulse width modulation. In the early 1900s, when electric vehicles first came out, we didn't have electronics. And we had to use resistances in addition to switches, which would flip various parallel arrangements of the battery cells to various speed. Modern solid-state electronics enables us to have pulse width modulation to provide continuously variable DC voltage without the power waste resistive elements. The pulse width modulation switches the battery voltage, which we're assuming here is 500 volts per second, on and off at a frequency of between 2 and 10 kilohertz. 2 and 10,000 times a second. And 0% duty cycle, this is the way the power would switch on, but it doesn't. So there's no voltage going to the motor. You remain at rest. 25% duty cycle, the pulse width amount to 20 for 1/4 of the time, and you get 1/4 of the average output voltage, which in this case 125 volts. 50% duty cycle, you've got half the voltage, 75%, and 100% duty cycle. There is no pulse width. There are no pulse widths. It's on continuously. Now, the voltage coming out of this then wants to go through a filter to smooth out the spikes. You get a smoother DC going into the motor. Now, electric vehicles also employ regenerative braking, which I mentioned before. Because of the symmetry of the Maxwell equations, among other things, a motor can also function as a generator. So some of the energy that the mechanical brakes replace this heat, friction, goes back to the battery. The circuits for this can be incorporated in the motor control. And when you apply the brakes, the automatic control system decides whether to use regenerative braking or to switch in the mechanical brakes. As the speed drops below the range where regenerative braking is effective, or when hard braking is necessary for a fast stop, or when holding the car at rest on a hill, the control system automatically then kicks in the friction brakes. Now, regenerative braking can be moderately profitable. In typical city driving, it can add about, where there's quite a bit of acceleration, deceleration, stop and go. It can add about 15% to your battery range. Where there's a lot of hill and valley driving, regenerative braking is most profitable and can add 50% to your range. On the other hand, when you're cruising on the highways where you almost never touch the brakes anyway, there's minimal benefit. Now, EV promoters often tout them as zero emissions, and this is pretty nearly correct. The battery charges from a green energy source. It's interesting, a few years ago, I met an acquaintance I hadn't seen for a while, and he told me, hey, I bought an electric car. And he commented how green it was. That time, the Duck Island powerhouse down in Trenton was chugging away, shoveling in coal and pouring out electricity and lots of CO2 and soot and all those other pieces. And I pointed out, I said, hey, so you're driving a coal-fired steam car, right? And he said, what do you mean? And I explained that to him. I said, oh no, we have solar panels and that's what we charge off. I said, okay, sorry about that. You are a good guy after all. On the other hand, even when using a combustion source, the efficiency is better than that of the gas car. And here we have a couple of graphs that kind of illustrate that. This is your typical gasoline car. 100% of the original fuel energy is what you start with. The energy blows off roughly 70% of it in lost efficiency. The accessories to the engine, which are necessary for it to go, like the water pump and the fan and all the other stuff, blows off another 4 to 6%. Drivetrain losses are another 3 to 5%, and a little bit for auxiliary electric use, like your headlights and such. So you end up with just about 16 to 25% of the energy you bought in your gasoline going to the wheels to make you go. Well, compare that with your electric. Here's one. We start out obviously with 100% of our original energy. We're not talking about how it's generated in the grid. We're accepting the electricity here is given. Let me get into that detail later. You do suffer roughly 10% charging losses or round trip efficiency of a storage battery. When you charge a battery and then take the power out by discharge, you don't get back all you put in because some of it has been lost as heat and other losses associated with the charging and discharging process. So if you put in 100 watt hours and you get out 90 watt hours, that's 90% round trip efficiency. The lead acid battery is about 85%, which is somewhat less. But the lithium ion battery, which is dominant in most modern electric vehicles, does give you about 90% round trip efficiency. And then you have, of course, your you do have your drivetrain losses and all that kind of thing. You still get out. Oh, and don't forget your regenerative braking. You still get out 87 to 91% of the original energy going to the wheels to make you go. Now, let us say that this 100% of original energy does come from a combustion power source, which a lot of our power still does. And so I've done a few little calculations here. Your conventional combustion power station, such as good old Duck Island used to be, runs a Rankine cycle steam engine, turbine, and then we don't always discriminate between the turbine and the reciprocating engine. We'll expand the steam, get you work out, which has an efficiency of about 40%. Transmitting the power through the grid blows up about 5%, so that's 95% left. And from the EV getting the power from the grid to the batteries and to the wheels is another 77%. So you multiply all these guys together, you come up with about 29% efficient. Considering the gasoline vehicle fuel to wheels is only 20% efficient, you've got about 1.5 times the efficiency of your gas car. Okay, let's upgrade our powerhouse. We're going to go to a binary cycle, or they also sort of call it a combined cycle. And here, you're burning natural gas, which by the way has less carbon footprint than hydrocarbons, coal, because a lot of the power comes from the hydrogen in the CH4 methane, whereas petroleum is CH2 polymers. And so that does give you a little boost. But let's just talk about the thermodynamic efficiency. The fuel first goes into a gas turbine, a Brayton cycle gas turbine, whose shaft drives a generator. The exhaust of that gas turbine is still hot enough to fire the boiler of the steam cycle. And that engine then contributes its part of the efficiency, and the combined efficiency, they're actually hoping to break 60%. So we'll just call it 58 right now. So it's double that of the gas car. Now, a major factor in electric vehicles is the so even when the electricity to charge your EV comes from the dirtiest coal-dominated grid, EVs still produce less global warming pollution than their conventional counterparts. The emissions for performance of the EVs will improve, of course, as our wind and solar power displace, and also some nuclear, displace coal-fired electricity generation. Many EV owners are also choosing to pair their EVs with solar panels, as my buddy did. And in that case, you're almost emission-free. By the way, EVs also have less maintenance and wear than gas cars, which we're going to discuss in a little while. Battery capacities. Lithium-ion batteries dominate the modern EV market, and we're going to see why. This chart here shows volumetric energy density, in other words, watt-hours per liter of volume, and the horizontal axis here is energy per unit mass, watt-hours per kilogram of battery weight. So the lead acid battery is not so good. Nickel cadmium is a little bit better. Nickel metal hydride is better still. And by the way, a lot of the conventional hybrids do still use the nickel metal hydride. Our Prius does. But at the top of the heap is in fact the lithium-ion battery. Not only do they have excellent round trip, not only do they have high energy storage, but they also have good round trip efficiencies, better than 98% at moderate charge discharge rates. They can, however, handle high currents with the rapid acceleration when needed, and when necessary, fast charging, or what would not make a habit of the latter because the battery doesn't like it and it will shorten its overall lifetime. Lithium-ion batteries used to be mighty expensive, but they are getting cheaper. This graph shows the falling cost of lithium-ion batteries from 2010, which is not that long ago, to 2019, so 10 years later. And you can see the price of the battery has dropped by more than a factor of 10. It's still dropping a little bit, or it's approaching some kind of an equilibrium. As our power grid evolves toward green and renewable energy, we're also going to adopt, I hope, smart charging. In smart charging, the charger receives information from the utility, telling it when the utility has a maximum available amount of green power. And you keep the car connected, and when that occurs, the charger turns on, and during those optimum times, the customer pays lower rates. But if you got to charge up now, because your battery's down, you got to suddenly discover you got to go somewhere. When the sources are not so green, then you will get sucked with higher rates. Already, Southern California Edison has set up a program where if you're charging an EV between 8 in the morning and 4 in the afternoon, when solar power, and California has lots of that, is on, then your rate is reduced. What are some of the reasons to own an electric vehicle? First off, it saves you money. No matter where you plug in, electric vehicles are cheaper to fuel than the gasoline-powered counterparts. Electricity provided in the largest U.S. cities also reduce rate plans for charging EVs. And the savings on energy cost, gasoline versus electricity, for the median average driving habits, amount of savings of over $770. Electric vehicles also save on maintenance cost. With no gasoline engine, they don't need oil changes, oil filters, spark plugs whose gaps need to be adjusted and periodically need to be replaced, timing belts that wear out, and you better replace your timing belt, because if it slips, piston's gonna come up when the valves are down and you'll blow the head off the engine, and then you're out of business. So there's a lot less routine maintenance. And these reduced maintenance costs can add up to $1,500 over the life of the vehicle versus gasoline. You're also going to cut emissions. That was my main topic. Even when the electricity, the fuel EV comes from the dirtiest coal-dominated grid in the US, say in West Virginia, EVs still will produce less global warming pollution than their conventional counterparts. I'm sorry. The average EV in the US today produces about as much such emissions as a gas car that would get about 73 miles to the gallon. And obviously the emission performance will improve as the power grids improve, replacing coal power generation by cleaning it. One thing that is often not mentioned, but you may observe it if you have signed up to drive an EV for this event, is a better driving experience. An electric motor, when starting up, produces high immediate power, high torque. The vehicles can not only make a jackrabbit start if necessary, but they also provide smooth, responsive acceleration and deceleration, largely because of the pulse width modulation controller. The heavy battery lives at the bottom of the car, so as to provide a low center of gravity. And this improves handling, responsiveness, and safety. A lot of these gas hog SUVs, when they suddenly have to make a fast turn or they get into a skid, they end up rolling over, which really can spoil your whole day. Electric vehicles are going to cut off petroleum dependence. Using gasoline causes numerous problems beyond just the emissions. As long as petroleum is our dominant energy sources, prices and availability are subject to global disruptions. Consider what's happening in Europe and even to some extent in this country as a result of the shutoff of exports of petroleum from Russia upon their invasion of Ukraine. Electric vehicles will help relieve such dependency. And as I pointed out, EVs are convenient to use and maintain. Instead of searching for the cheapest gas station, you can plug in at home at a cheaper and more predictable cost. So you plug in at night, you can wake up in the morning with a full tank. And unfortunately, this is not going to be so simple for those who live in apartment buildings, but if you manage a starting charging stations in the parking lots, you hope more will do that. And since the battery electric vehicles are mechanically much simpler than gasolines, so once again, maintenance is simpler and cheaper, as described above. It's also likely that public agencies, which already offer subsidies to buy such vehicles, are going to encourage EVs with privileges like access to special access lanes on highways and special parking spots, the free-mode parking spots. And these may be the parking spots next to charging stations, and reduced or free tolls on toll roads. Well, it ain't all gravy. There are problems with these. And let's go through some of those. First off, we're going to have to figure the power grid is not yet prepared to handle all the EVs, even with smart charging. The further load we're going to see in the near future is more electricity used for home heating as we switch over from combustion furnaces to electric heat pumps. So we've got to rebuild a lot of our power grid anyhow. The entire community of electric customers will initially bear this expense, although in the long run, it should be paid back by the savings that everyone enjoy. There's a question also, the stuff to make lithium batteries out of. Lithium batteries not only use lithium, but also nickel, cobalt, manganese, and graphite. Some of the metals for lithium ion batteries are relatively scarce. At least they don't occur in high concentrations in the Earth's crust. So you have to dig up and refine a lot of ore to get the desired amount of metal. Now, such mining can cause serious environmental damage, especially in places with lax regulations. There's also the problem that mining and manufacturing in some countries already involves unethical practices. Child labor, excess hours, forced labor, and unsafe working conditions. Recognizing the public concern about these problems, some countries have agreed to more traceability of their mining operations and refining operations. Right here in New Jersey, there's a company called Optel, which is offering a traceability service to those in the lithium battery industry who want to assure their customers and business associates that their sources and methods are clean and ethical. Unfortunately, as we know, not all businesses, not all countries are going to play by these rules, but as more and more do, perhaps the pressure on the outliers will become stronger and they'll join in. Recycling and salvage of worn-out batteries is probably the most obvious problem that has been raised in the literature. This is not yet an established industry, but we must get a system in place before large numbers of the first generation of EV batteries reaches the end of its life and have to be and have to get scrapped. The estimated lifetime of lithium-ion batteries is 15 to 20 years, which is about 3 times that of lead-acid batteries. Although lead-acid batteries already have an almost perfect recycling system. When you buy a battery for your car, a cranking battery, it's going. You pay a deposit. Price has a deposit, and when you turn that battery into a dealer, you either get that deposit back or it gets deducted from the price of the new battery. It's not obvious, but it is included in the whole business. And the battery, the lead does get recovered, both because it's valuable and because it's ugly. Optimally, the design and manufacturing of a battery pack should consider its eventual recycling. For example, the materials that you make it out of. There's a polymer plastic called PVDF, which is standard polyvinyl iodine fluoride. It's a binder that holds parts of the cell together, but it's very difficult to break down chemically. So battery makers are starting to switch over to plastics that are more adaptable to that kind of service. It would be helpful also if we could standardize battery design and construction to facilitate disassembly, especially if we decide to perform this in an automated operation. A little aside here in battery life, even when a battery is no longer suitable for the high current full capacity needs of an electric vehicle, it may enjoy a second life as for energy storage and less demanding applications, such as leveling grid demand, or in households or businesses that are off-grid and generate solar power, which they then need to use during times when the sun isn't shining. But eventually, all batteries are going to get scrapped. And when this happens, we've got to make sure it does not end up in the landfill. By the way, that's a polite name for a dump. Now, even the delays associated with roadside charging, say you're taking a long trip beyond your battery range, you pull into a station where you're supposed to recharge your battery, you're going to have to maybe wait in line to get a chance to charge, and even then it's going to take a half an hour to an hour to charge yourself up. Some people consider the possibility of battery swapping, although this would require standardization for a limited number of battery types. The battery would belong to the battery company, And one would pay a recharge fee for the swap. You pull into the station, a jacking mechanism lowers the battery out from under the car, takes it away, puts it on a charger, and shoves in a fully charged battery. You pay the charging fee, and you're underway. The total time is no more than it would take necessarily to fill up your conventional car with gas. And once your battery is, the battery you gave up is fully charged and ready for another customer, it gets put into his car. This is not in principle, by the way, different from deposit bottles or the way industry has for many, many years and still does deal with compressed gas cylinders. Another way to mitigate roadside recharge problem is to minimize long auto trips with better public transportation. Also, we hope electrified, such as one finds in the advanced countries. If one then needs a car at the destination, you have economical rentals of short-range electric vehicles. Looking into the future, let's see what's many of these problems we talked about are associated with the lithium-ion batteries. So there are alternatives. Last November, the Thomas Register, which sort of not only directory, but also writes articles about American industry, described a whole bunch of batteries that might possibly replace lithium ion. I selected a few that seem the most promising, and I'll talk about them now. There's a saturated salt aqueous magnesium battery. Dennis Leung and his crew at the Department of Mechanical Engineering at the University of Hong Kong are working on this. Magnesium is the eighth most abundant element in U.S. crust. It's non-toxic and being bivalent, that is, it's in the second column of the periodic table with two electrons available for chemical reaction. It may even have a higher charge capacity than the monovalent lithium, which is the first column. And as I said, it's also cheaper and safer than lithium. There's also a solid state electrolyte, which is also called a solid state battery. The NASA Glenn Research Center is working on this. It offers an even higher energy density than lithium. This is an entirely different sector. The Toyota Motor Company is on track to roll out in 2005 an EV with a solid state battery. They hope to achieve full charge distance of about 400 miles and accept full charge in less than 20 minutes. And once again, it would have increased safety over the lithium battery. And finally, there's the graphene battery. Graphene is an interesting material. It's a carbon monolayer, carbon atoms, tightly bound in a hexagonal honeycomb lattice. By the way, there's a lot of tensile strength. It can, however, be stacked up to make the material practical thickness. Graphene battery technology has been demonstrated in the lab, but only recently has there been evidence that a practical competitive to lithium batteries is possible. The Graphene Manufacturing Group, GMG, paired with the University of Queensland, Australia, and a company called UniQuest, are working to develop graphene aluminum ion battery. And any of those, or perhaps all of those, may enter the market as competitors with the lithium battery. All of this combined with a smart grid. Here we have growing the smart grid and the green sources, wind, photovoltaic, hydroelectric power, pretty green in the sense of no CO2 emissions, but with its own, a few of its own problems, nuclear power. And there may still be a few thermal power plants kicking around, and the power then will go to cities and buildings, factories, homes. Look at that guy, he has a solar panel on his house. And of course, electric vehicles. And we're hoping that they will become the dominant road vehicle in this country and possibly the rest of the world. And so that about wraps it up. If you have any questions, let's see what we got. Yes, please.
You have an estimate for how much additional electric power generation would be required say, by the time we have 50% of the cars electric on the road?
Unfortunately, I don't have a number like that, but, I actually should look that up. Yes, please.
I do. The estimates are around 20 to 30% extra power generation.
Well, thank you.
Yeah.
Thank you.
At the point, but 50% of the cars, or when all?
Yeah,
Okay.
with 80% penetration, we're looking at 15 to like around 15% additional.
Okay.
So it's nothing horrendous.
No, and in fact, our generating capacity in this country has been growing steadily the past decade and our use has been dropping. So it's
Yeah.
super feasible.
Thank you.
Thank you, that's very good. Yes, please.
Might have missed you saying it, but when you charge and discharge a battery, you have losses.
Yes, sir.
So if you put a kilowatt into a battery charge, you
Kilowatt hour,
don't get a kilowatt hour out, you get less.
you get 90.
What does the lithium ion and the automobile batteries do on their round trip?
90%.
90, so they lose 10% of the
They
energy.
lose about 10%. A lot of it depends on the charging rate. If you take a lead acid, you just at home, if you take a lead acid battery and you connect it to a charger and charge at a high rate and you feel the battery after it's been charging for a while, you're gonna feel it's kind of warm. If you charge it slowly, it's not gonna be significantly warm. So a lot of the round trip efficiency is a function of the charge discharge rate.
Oh, so if you do a fast charge, you'll lose a little more.
You lose a little bit more, and also the battery will not like it. Lead batteries are very finicky little fellows. You fast charge those guys too many times, and you're gonna lose it.
The lithium ions that have the fast chargers programmed by these companies, they're actually sacrificing some lifetime.
Possibly, well, the charger, the home charger is not gonna charge you up in half an hour. You're talking about the charges that might be at roadside stations where you have to get back underway as fast as possible.
So the home chargers that charge what? At 40 amps and 240 volts is medium speed at best.
Yeah, I think those are pretty okay. Yeah, those are not gonna.
So that the high speed chargers are actually pumping more like 100 amps into your battery.
I'm gonna get something like that, yeah. So it's not something you wanna make a habit of, but if you're stuck in the middle of nowhere and you gotta get rolling again, you may wanna do that. I'd say it's not terrible, but you just don't wanna charge it all the time like that.
Ideally, you probably don't want to run out of electricity before you get home.
Then
Run out that you need to charge a battery. Just get home and put it on charge.
that's what you like to do, yeah.
Which means you're really, commuters and local driving, but your tour of the Western United States is probably not going to be big on your list.
It may not be, although as we get more, you may be able to choose at the station,
But let's say not big on your list this year.
Say-
Maybe in 2031, it may be atop of the list.
But, and maybe these charging stations, you can choose whether you want a faster charge or less aggressive charge. Yes, ma'am.
Actually, I was going to suggest the tour of the Western states is going to be depending on the infrastructure, which is where electrical vehicles being adopted by post office, by taxis companies,
Oh, yeah.
or buses. They'll basically build the infrastructure to service their fleets. And then will be trickled out from that, hopefully.
I hadn't thought of that. Yes, that sounds like a very, very good
Okay, but-
possibility.
There's also a
You're saying there would be some charging at those locations, or they're just driving the supplier of electricity to support more?
driving the supplier of electricity to support more, getting infrastructure built so that the cost per unit goes down because there are that many units out there.
Oh, okay,
So-
just
so
volume of production of the.
Volume of production of the equipment. Unfortunately, there's a bit of kickback. I think in Mississippi, they're talking about banning electrical vehicle dealerships because it's bad for the gas business. Also, certain states are considering, okay, the electrical vehicles are not paying the gas taxes, which is what is supporting the roads. We should make the electrical vehicle more expensive to register because it's no longer hiding the cost of the road upkeep.
I see, and the next time Mississippi gets sucked with a category 5 hurricane that wipes out,
Well, they've
wipes
identified
out 8
a
cities,
real lot of
cities at a cost of $1,000.
Every mile in a gas car is helping to pay for roads, and electric cars aren't doing that. That's a disparity that needs to be resolved
And
on
they're
a fair
trying-
basis.
We're trying to address it by raising the cost of registering the electrical vehicles.
Yeah, but that's the wrong avenue. They really need to build it into per mile.
Or build it into the electrical charging vehicle,
Yeah.
electrical charging vehicle.
So the public chargers could be built in, but the home charger would be more difficult.
Well, it could be seen as if you live in what our former president called an S-hole state. I don't know if you can hold that as an example of what things should be, but a lot of states may say, okay, if you're driving an electric vehicle, the good you're doing for the environment is something that should be rewarded, so you're not gonna get socked with gas tax. But that may be what advanced countries are doing too. I guess it is an interesting problem. I'm not sure how we're gonna resolve that.
Can I ask you a follow-up question to your comment about the long-term battery degradation when using high-speed charging?
Yeah.
So most of the manufacturers, the automobile manufacturers, recommend that if using high-speed charging, cap out at 80 to 90%. How much does that mitigate the degradation over time?
I'm not sure of that. Are you talking about lead batteries or
Lithium-ion.
lithium batteries? Yeah. I don't know about that. That is something that I guess I should look up. The consequences of fast charging on the lithium-ion battery are not as bad as on the lead battery. The sort of weaknesses of the lead acid batteries, one of the most famous commentators on that was Thomas Edison, and that's why he invented the nickel iron known as Edison battery. There's all the complaints about the noxious behavior of lead acid batteries. They're very finicky. If you leave one in a discharge state for a while, if you overcharge, it doesn't like it. If you undercharge, they're really finicky characters. Yes, please.
Yeah, one problem that I see with the electronic vehicle is the charging time is too much. If you go to a gas station right now, in a few minutes, you can get your tank filled and you're ready to go.
That's right.
Yeah.
That is a problem, and there's no fundamental way to beat that. Even if you get charging down to 15 minutes, it's still a hell of a lot longer. Although I suppose, for instance, if the charging station was tied to a restaurant, you could get out, take a pee, have a cup of coffee.
Correct. I mean, that's another way of.
If you did a terrible sin, you need to punish yourself. You know that.
I'm thinking of the Oasis out on the turnpike.
Yeah.
And they're isolated and they're great distances apart, but people pull in, they gas up, they park, they go in, they buy some food, they pee, they do this other stuff.
That's
and they
exactly what I
finally
said.
leave. They've wasted 20 to 30 minutes total time.
Yeah.
And if they can design and structure that Oasis so that you can immediately start charging, go off and use the toilet, and buy the food and do the stuff and relax and unwind, do what your stuff. And you're happy and you come back and the car's done.
Yeah, that's exactly what I suggested
And,
here.
and at that point, it's fast enough.
Yep.
And this gentleman here talks about don't fill them up to 100%. That's always been known even with the cell phones or laptop batteries is don't charge them up to 100%, charge them up to 60 or 70 or 80%.
Yeah.
And with the smart charging and the cars going on, they can probably push it to 80% and
Interestingly,
maybe keep the temperature of the cells below a threshold that they will have no sacrifice at all.
by the way, the lead acid battery is the only battery I know of where you can tell its state of charge without knowing any history. It's the only battery I know of where you can know its state of charge walking in blind and not knowing anything. Ma'am, go ahead, I'm sorry.
No, it's okay. I was just gonna say that actually like around 80% of charging happens at home. So most people, they're just waking up with a full charge. So they don't have to stop at a gas station.
That's exactly what I said. If you use it for commuting, remember, you got about 300 mile range in a typical modern electric car. Which is about what you get on a gas car and a full tank of gas. Yes, please.
So you talk about Brunswick DC motor. And that's Tesla company. Which companies are using those motors? Why are those not?
I'm not sure. I think it's my understanding that gradually we were switching over to the brushless DC motor. One minor problem with the brushless DC motor is there are permanent magnets in the rotating armature. Those magnets have been quite strong. So they use rare earth metals to make those magnets. And that can add to the cost of the motor compared to the induction type AC motor. But once again, the induction, the regular frequency three-phase AC motor requires a much more complicated pile of electronics to run it. And that sort of narrows down the difference in cost. And by the way, it would involve a small sacrifice of efficiency, but you know, for the last 130 years, we've been generating fields motors with wound electromagnets. In other words, instead of having permanent magnets, we have coils, they pass DC through them, and you would have to have some kind of brushes and slip rings to do that. But the current will be very minimal. They might affect the efficiency of the battery life.
This is going to be the last question. Last question.
Okay, please. I'll let somebody who hasn't asked one yet.
You hadn't asked one.
Yeah, if you have a question.
No, I was going to just say you're 2 minutes beyond the official stop time.
Oh.
Take the walk to get to the next spot.
Yeah,
There is an official. Not beyond it.
yeah, maybe we should wrap it up then. Thank you very much.
Thank you.
Thank you.